Hello, my name is Vince Mallette from Focus Microwaves, and today we're participating in FormFactor's webinar on advanced millimeter wave load pull and noise parameter extraction. First off, I'd like to thank FormFactor for inviting us for this event, and we've been a partner for many years, and today is just an example of the collaborative work we've done throughout the past few years. So let's jump right in it. I have about 20 minutes today. So the agenda for today, short introduction. We're going to cover some basic theory of noise parameter extraction. We have different examples, 50 and 110 gigahertz. Also, then I'll go through a step-by-step calibration process because a lot goes into this process, and noise measurements are very intricate, and all these steps need to be very well respected to get the best out of your noise parameter measurements. We'll talk about impedance patterns, how that affects the performance as well, and tuning range. We all know how important tuning range is for passive tuners, especially in load pull, but we'll see how it applies to noise as well. Then a bit of sample data throughout the presentation and some final notes on best practices. So a quick introduction to Focus Microwaves. So, we have three main silos of activities. We obviously have a large portfolio of passive tuners, wideband fundamental and harmonic tuners. We have our pulsed IV and our modeling as well. Today we'll be focusing more on the passive tuner used for noise measurements. So we've been a Keysight solution partners for about 3 years now, and in this presentation we talk mostly about how to use PNAX and the noise figure option within the PNAX. But obviously we support other options, for low pull and pulsed IV. But as I mentioned, we'll be focusing more on this aspect of integration with the Keysight equipment. So let's talk about noise figure and noise parameters. So noise figure, if we look at it in the time domain, the way we have to see this is we're looking for the additional noise our amplifier is generating. So we want to characterize that. Okay, so obviously an ideal amplifier would simply just amplify the signal, therefore increasing the amplitude and not really adding anything more to it. So in the real world, we know that the signal that's actually coming in our amplifier is not a pure sine wave. It has some noise tied to it, and obviously the amplifier will add its own noise as well as amplifying the signal. So the ultimate signal in the end will be increased in amplitude, but also will have other artifacts or other components to it. If you look at it in the frequency domain, this we're showing the equation at the same time, but basically this is what we're seeing. The amplifier doesn't discriminate, the signal, the carrier signal, and the noise. It basically amplifies everything coming into the input, and you'll see it at the output. And that's what we're trying to see is like how much added noise is our device providing. So when we talk about noise parameter, we talk about extraction. We don't say, I'm just doing a noise parameter measurement. I am doing noise measurements and then doing an extraction to get the four noise parameters. So the four noise parameters are minimum noise figure, the equivalent noise resistant, also known as RN, and gamma op. So gamma op has amplitude and phase, so that's why we say there's four parameters in total. So if we have this graphical view on the right here, so basically there's NF min. So the minimum noise figure is the lowest noise figure you'll get at a certain impedance. So at that point, we also call that gamma op. So the optimum impedance for the lowest noise figure. Now from that point, the noise figure will only increase. So as I move around on the Smith chart, that value would only go higher. So theory says that you need 4 points to extract the four noise parameters. So in other words, you need 4 measurements to solve the four equations that will basically allow you to extract that. In reality, you need much more than that because some points overlay, some points are very noisy or very far from the optimum point. You might fall in an instability region. So ultimately, we over measure to basically get more results, and then we use more points than just 4 to actually get a decent extraction. So that's, but again, based on these measurements, the goal is to create this surface. So if you're familiar with load pull, usually this surface is the top point is at the top because we're looking for the maximum efficiency or the maximum power. In this case, it's inverted, so it goes upwards, and because basically we're looking for the minimum point. And at the end, we're looking at the RN, and basically that tells you the rate at which the noise figure is actually changing as you move away from the point. So a few millimeter wave examples. So everything I'm telling here, we'll say in the following slides applies for like the RF applications or the millimeter wave applications. It's just the point is stronger, or that you have to put more importance on these different steps when you actually go to millimeter wave, because the loss is higher, the uncertainty, the dynamic range, all of it becomes a bit more difficult to manage. So you need to make sure you address all these points adequately. So this is a full setup diagram, obviously. So we have our network analyzer and slash noise figure analyzer, so VNA and NFA. And what we do is we basically have two paths. So there's an S parameter path. So that path basically goes here through a switch matrix here, through the tuner, through the device or the different calibration standards that we'll put, and then goes again through the switch, and that's your S parameter path. Now, if you want to go through the noise path, you're going through the noise source, again through this switch, and now we're not going upwards, we're continuing, going through this switch, going through the LNA, and going to the noise path. So you basically have two distinct paths, S parameters and noise on the VNA. Okay. Here on the right, we basically have the equation. We'll dive deeper into this, but this is just to kind of show how the different terms affect the total noise figure of when we create these measurements. The noise figure of the DUT and the gain of the DUT, as well as the different noise figures of the different paths and the instruments, will have a different impact depending on how you configure them and to get optimal results. Okay, so here's a diagram with some real components in there. So here in this case, this is probably our most popular tuner that also covers RF, not just millimeter wave. So this is a 2 to 50 gigahertz. So this is a very wideband tuner that most foundries in the world use for this device characterization. So as you can see, we have very good coverage from 2 to 50 gigahertz, and this tuner actually connects directly to the probe. So this tuning range is very high, even at the DUT reference plane. And again, we have the setup here where we have our PNAX and the different paths from S parameters to noise. Now, once you go higher than 50 gigahertz, you run into not an issue, but a challenge where the VNA basically receivers are limited to 50 gigahertz. So you can't just use the same architecture. You have to basically split this signal and then down convert the signal so that the receiver can actually see a signal that's in the frequency range it can operate in. So in terms of S parameters, it's pretty straightforward. Keysight has this broadband heads that basically allow you to go pretty much very low hertz up to 120 gigahertz. So that's a path, the S parameter path that we know here, so that doesn't change. Now, what does change is when you go higher in frequencies, then you could run into some banded solution, and where in this case we were able to do 60 to 90 gigahertz, coax components here, but some waveguide components on the output. So this can be limited in terms of waveguide, but there's a lot more coax components that are coming out on the market. So we're seeing more and more possibilities in that sense, where we don't necessarily use waveguides. We can use couplers and to kind of split out the signal. So there's different capability there, but we really like to leverage the fact that the tuners are coax and they mate very well with the head. So now we just need to figure out the down conversion part of it to kind of match the receivers of the PNAX. And on the right here is just a small example of a setup. This is actually for load pull and noise. So the tuner, there's a tuner on the input and on the output, and they're connected directly to the millimeter wave heads. So here's a step-by-step. So in our software, we have a wizard, and basically just walks you through the different steps of setting up a system and calibrating the system correctly. So this is a small video, so let me just start it. So the first step, we're just configuring the instruments, and as we know, the important instruments in this case are the VNA and the noise figure analyzer. So those are the two, it could be an external noise figure analyzer or an internal noise analyzer, depending on what you're using. So once you've gone through this step of identifying, just configuring all the instruments, then you could go and really get into the calibration steps. So one of the first step is what we call our 3T standard standard measurement. So what we're doing here, so I just stopped the video real quickly. So what we're doing is we're pre-characterizing 3 standards that we're going to be using at a later stage. So, so here we're basically just measuring the 3 S parameter files, or S1P files basically, and this will basically be used later. Okay. Now again, here we're configuring the S parameter path from the VNA, and this is where when we're going to be measuring the device, because we need the S parameters of the device at one point. So now we need to do an on wafer calibration. So the software basically configures the VNA and the switching so that we're going through the S parameter path, and we're able to do an on wafer calibration. So when we do the S parameters, we're really at the DUT reference plane. Okay. Now we do a 3T S parameter measurement. So in this case, the goal here is to be able to represent the S parameters. So basically we're going to present our 3 standards here and de-embed and basically measure through this path, and we're going to be able to de-embed this section here. This is going to be used at a later stage when we're going to do the KBG calibration. So this is basically used so that we can shift the reference plane here once we actually calibrate the receiver. We want to be able to make sure we're not generating the KBG here or the ENR at this point. We want to kind of shift it to this point so that when we calibrate the receiver, we're actually calibrating it at the right point. Okay, so we basically just remeasure the files and or input the files, and just it will calculate the S parameters required. Then another important point, we're cascading all these different paths here. So what's very important is we also need to know the impedance of the source here and as well as the receiver. So what we do here is, again, we're just switching the different paths and measuring the one port response so that once we cascade the tuner and cascade all the different components, we have all the right components to cascade it correctly. Then an obvious one is a tuner calibration. So here in the software we simply define the start, stop, step frequency, and that will basically step through all the calibration points that you need to perform the measurement. Okay, then we get down to the KBG cal. So again, now you just need to import the right file, and then you just launch the KBG cal. So that's a 50 ohm measurement, which is a hot cold measurement, and basically at 50 ohms, and that will be used in the future. So now we get to the noise receiver calibration. So the noise receiver calibration is important because now we need to define a set of points that the tuner will actually go. So we're actually going to tune the tuner at different points and measure the noise or the noise performance of the receiver. So the pattern of point is important because as we move up in frequency, these points will shift around, and at certain frequencies the point distribution can be very good, but it can be very bad at other frequencies. Okay, so we have the capability to have a low density, a high density calibration. So but that is basically pre-characterized or predetermined ahead of time to make sure that we actually have a nice distribution of point, not just at one frequency, but at multiple frequencies. Okay, so now we're kind of skipping a step here. We're just going to show like the end result. So here's a 4 to 50 gigahertz measurement. So this is the noise figure. There's no smoothing. This is really kind of the extracted data here. This is usually the smoothing that we use. It's we call it a wideband optimization, and you could kind of take it up a notch or bring it back down. But basically, you want to see a smooth transition from low frequency to high frequency. And here we're going to kind of toggle or drag this marker here, and what we should see is noise figure surface should basically increase, so it should go higher as we start increasing the frequency, but it's also shift, so the phase shift should follow the trend of gamma op. That's going to basically start increasing and going to the west side of the Smith chart. So let's just click on that. So now let's take a quick view. So we can see the optimum point is here, and as we increase in frequency, this optimum point should be shifting in this area. So not only shifting in this area, but it should also increase. So let's get a visual of that. All right, so now we're going to sweep the frequency. So again, the marker is increasing here, and you can see that that's following in this case and shifting in phase. Okay. So now let's get into a bit of the equations. So before we get into one application note we strongly recommend is this one from Keysight. This is kind of an application note that's been around for years, even in the Hewlett-Packard days, and basically kind of evolved, with the new instrumentation. Very useful information in there. I refer to it in the best practices as well. In here, it discusses how the multi-stage noise figure contribution of the different stage impact the performance and the measurement. So here again, we've kind of looked at this equation here. So we're going to go a bit deeper on the next slides. But basically, what we're trying to show here is the noise figure of the system is a total of these, or the summation of all these different equations, or these different ratios here. But you could see that the main contributors are going to be the F1, so the first item in the path, this and the gain of it as well. So if the noise figure is high here, you know that regardless of what's happening here, the system noise figure will be high. Now these components here will be affected by the gain. So if you have a large gain, this component is going to be small, this component is going to be small. So ideally, you really want your first item to have a small noise figure and a very large gain, and that's going to allow you to have a very low noise figure and a very sensitive system. So I often get the question, do I need an external LNA? Our systems comes with these external noise modules, and basically those are switches. There can be a bias T inside, but the big component is also an LNA in there. I'll get the question from my customer, well, we just bought this brand new PNX. It's great. It has all sorts of great performances. Isn't that good enough just to measure noise figure? So the answer is no. It is a very good performing instrument, but we need to reduce the noise figure of the instrument by adding an LNA. And this is, if we look at some real numbers, we got to understand quickly why this is. So this is the noise performance of the PNAX at different bands of frequencies. So at the lower band, it's roughly 15.5, but in the bands of interest, let's say 5 to 50, we're in the range of 16 to 18. So let's call that 16 for this example. So noise figure equations are mostly in linear. So now you need to convert this to a linear number, right? So just here's the math to convert it. So a 16 dB noise figure translates to roughly 40 in linear. Okay. So now again, if we take a look at the equation that we use, we need to input these values. So what are the values? So we have the noise figure of the instrument, which we just calculated, is 40. 16 dB translates to 40. And then we have the noise path, all right? So because here, basically, this is part of our receiver. So that's the second component in our system, okay, and in the equation. So we need to put that in the equation. So what happens in this case is there's no gain. There's only loss because this is an RF path, and it's depending on what frequency you're operating. It could be higher, it could be lower. So we know that the equivalent noise figure of a passive component is equal to its loss. So 3 dB attenuator will have 3 dB noise figure. So, but as we translate that, 3 dB translates to 2 in linear. Now the gain is 1 over the linear value. So let's say in this case it's minus 3 dB. So what happens in that case? That becomes 0.5, right? So if we put that in the equation, now we have a noise path of 2. And if we put the noise figure of the instrument of 40 minus 1 divided by 0.5, this comes to 19 dB. So, or 80 and 19 dB if we translate it back to noise figure. So this number is greater than this, and it makes total sense with what we were calculating. The noise figure of the analyzer is 16 dB plus the 3 dB loss of the path comes to 19. So the math makes sense. So, this is not as accurate or as sensitive as we'd like it to be, and especially in 3 dB, that's at low frequency. But as we increase, to 50 and 110, that number drastically increases, and that becomes an issue. So how do we reduce this number? So again, we looked at the equation. The goal here is to reduce this number here and increase this number. So how do we increase this number? Is by, in the noise path, we need to increase the gain of the noise path. So again, if we take the same numbers, the instrument noise figure will not change. We need to change the path and the gain. So by putting an LNA here of roughly 30 dB, 30 dB in linear becomes 1,000. So now we go from the 19 dB value, we could reduce this to 9 dB. So this becomes way more interesting and way more usable. Okay, so basically that's how we have to understand why the LNA is used in these kind of setups. So here's a quick example. Now what we're doing, I just used I copied the same image with the same equation, but here what we're doing is that this is an example receiver cal, and we're going to do the same thing. We're going to sweep the frequency, and as we sweep the frequency, we're going to see this noise figure kind of jumping around, and what that's basically doing is we're doing like, let's say 0.5 gigahertz steps or 1 gigahertz steps, and it's basically turning around 50 ohms. So it's not as smooth as like on a transistor where we're actually at gamma op when we're high on the Smith chart. We're just kind of like turning around 50 ohms, so it seems like it's moving a bit, but you can see that the values are still relatively low. Even to 50 gigahertz, we're in the range of 12 dB. So let's just run that. So you see we're just slowly increasing the frequency range, and you can see that we're still getting the low values, and we're jumping around near 50 ohm, and the values are relatively still relatively low. Okay, one thing to also worry about is the stability of the device. Now, the stability circles are basically directly related to the S parameters of the device. So when you have an S parameter of a device that looks like this, you know that the S parameters are going to be like kind of like on the high end side here. So what this circle identifies is this is a potential unstable area. So as you tune the tuner, you don't want to be in this area too often. It's not because you are actually there that it's going to absolutely oscillate or be unstable, but potentially it can be. So you can see here as we move in frequency, we're plotting gamma opt here. So as we move here, we see that the stability circles are also moving. So when we're going to be moving the tuner, we have to be cognizant of the fact that we could actually fall in a instability region, not necessarily at the measurement frequency, but at a higher frequency or at a lower frequency. The device sees the entire whatever we're presenting to the device. It's not like in low pull, for example, that's looking at a single impedance here. In noise, it's a very broadband measurement. Instability regions are very easy to hit. Okay, so now we get into like tuning range, where some customers might say, well, tuning range is very important for load pull, I get it, but for noise, this is a linear extraction, linear measurement. Do I really need to have very high tuning range? And so our answer is always like, yes, in using passive tuners, you never have enough tuning range. You never want to limit it. But here's a small example. As we've mentioned, like here's like the gamma opt at low frequency, but as you increase in frequency, the gamma opt will still stay high. So you do need high tuning range, not only at lower frequencies, but at high frequencies. Here's an example of the tuning range at the low frequency. So the low frequency, clearly you have no problem. You have a very good coverage, so you'll be able to present all sorts of impedances, kind of far away from the instability region. But as you move higher in frequency, so now this is like the operating frequency that we're trying to tune impedances. Well, you can see that if you don't have enough tuning range at the high frequency, you're going to run into issues. You won't be able to go past the gamma opt. You're going to be far from the optimum point. So this will hinder the capability of being able to reach the optimum points and to basically close those circles. So here I tried to represent it on like how the impedances shift in frequency. I have an animation after, but I'll try to explain it here first. So when we do a distribution of points at a given frequency, so here we have a nice distribution of points. We have a point that's close to gamma opt, past the optimum point, far away from the instability region. We also have a point that's also kind of in mid-range, one that's a bit further, one that's much further. So this will give us a good distribution of points to extract and create these surfaces accurately. But as we move in higher in frequency, what happens is those impedances are going to kind of shift in frequency. So this are like the potential trajectories as we go in frequency. So in other words, we don't move the tuner in this case, but as we sweep in frequency and we sweep the measurement, the impedance seen by the device will change drastically. So it will start here, but then end up at a different point. So this is the end point. So again, this was at let's say 2 gigahertz, and this is like roughly 40 gigahertz. So what we're seeing here is now the same distribution of point is very different. We have 2 points very far and a lot of 2 points very close and a few points very far. So now you have nothing in the middle to kind of curve fit this accurately. You just have two points. So that's going to basically give you a line that's going to be very difficult to curve fit. So we do a lot of measurements. So sometimes this is not really a problem, but it could be a problem if you have this recurring situation on many frequencies. So here's an example. Again, in the software, we allow the user to define different point distribution. So here's a point distribution. You can see here at the beginning, we have a lot of points. We have a lot of green points. So what that means is the measurement is matching the extraction. So we basically can set a threshold. And what we're seeing in this one, as we click on it, so we're at roughly 30 gigahertz. So as we're measuring the points, the point distribution is good. The optimum point is in the middle there, and we have points past the optimum point. So this is an ideal point distribution. But as we go lower in frequency, we'll see the points start shifting around. And what we're going to see here, we have some blue points, some red points. So we're seeing more and more points that are kind of failing, that are not matching the measured and the extracted data. And you can see that at the end, when we get to the like 10 gigahertz-ish, we're getting like a very poor distribution. Now we're not even close to the optimum point, and we're all shifted on one side. In this case, the points are still green, so we're getting good results, but this is not something that you want to have happening on many frequencies. Here's another example where the point distribution is just better. We made a better selection of points at the beginning, and now when we shift in frequency, the point distribution stays more even, and even at the lower frequency, we have a very good point distribution across. So you'll see a few points that still fall in the blue and the red, but most of the points are green across all the frequency points. As you can see, we have some points that are very close to the optimum point and some points that are past. So that's an ideal point pattern. So how do we do this? The high frequency delta tuners that we've come up like about 3 years ago, have been extremely popular for load pull because they were capable of taking the tuner and connecting it directly to the probe tip. So traditional tuners are very similar, use the same technology, same type of probing and things like that. But we can see that here there's no way to connect that directly to the probe. You need to add a cable, and this loss will basically limit the tuning range of the tuner. So in this case, we've totally eliminated the cable, which allows you to get the best tuning range as possible. So this will allow you to not only get good tuning range at lower frequencies, but at high frequencies. And if the tuning range is too high and you are hitting those instability ranges, well, you could bring it down. It's always easier to bring the tuning range down than to bring it back up. That's something you can't do in noise. So here's just a quick example. You see that this is like a poor tuning range, and this is a better tuning range. Probably slightly exaggerated, but it's just to kind of show the example. So final notes, best practices. This is just one quick slide. Shielded room, we can't mention this enough. Shielded room is something that some customers try to, it's an expensive investment, obviously, but this is something that if you want to get into some low noise, serious noise measurements, this is something that you absolutely need. With everything that's, with all the cell phones, the Wi-Fi, the interferences that we have these days, it's almost impossible to get accurate noise measurements without being in a shielded environment. Then I refer again to the fundamentals of RF microwave noise figure measurements from Keysight. It's just a really good step-by-step document that helps you choose the right noise source. Worry about mismatch of noise sources. A lot of customers don't they take whatever noise source that's hanging around. So when you do 50 ohm measurements, you might use a different one than you're using at 50 gigahertz when you're doing noise parameter extraction. Some of them have 6 dB ENR, some of them will have 15 dB ENR. So you need to choose the right ENR source. You might need to recalibrate sometimes if you want to hit different frequency points. As the noise source is calibrated at given fixed gigahertz, you might want to have some points inside so that you don't have to interpolate. You could basically get that pre-calibrated. So they go into that quite in detail. Choosing the right receiver, that's an obvious one, and really doing a dynamic range or a noise budget. Because what ends up happening is you have limitations in terms of dynamic range on the receiver. The LNAs that we use also have a certain dynamic range you need to respect, and so does the device. So you really need to budget that correctly. You can't just mix and match anyone and hope to have, from 2 to 110 gigahertz measurement in a smooth curve. You might have to divide that band up. You might have to choose some right attenuation. So there's a lot that goes into it before you actually do the measurement. Because I see this a lot of time. Oh, we see a saturated curve, like, oh, what's wrong? The system's not working. But in the end, we just need to do a bit of more analysis ahead of time to make sure that we budgeted the dynamic range correctly. So that was a quick overview. I tried to cover as much as possible in less than 25 minutes. If you do have additional questions, we have, you could go on our website. We have some frequently asked questions that are available that can help you there. But, you're more than welcome to sending me an email as well, vince@focus-microwaves.com, and I'll be glad to answer any questions you may have. So thank you again for watching, and I hope to see you soon. Thank you.